Electronic gearing is based on a similar principle to physical gearing, but is done electronically without mechanical linkage. With electronic gearing, there are slave or follower axes, which are the axes being controlled, and a master axis. The premise behind electronic gearing is fairly simple. The master axis motion is measured, and this output becomes the input for the follower drives. The follower's move is a function of the master's move and the gear ratio, which defines the change in the follower's position related to change in the master's position. One advantage of electronic gearing is that the gear ratio can be changed as needed with a simple variable and can even be programmed to change within a move profile. This is an advantage over mechanical gearing, where adjustment to the gear ratio requires mechanical change, which are costly and time consuming. Another advantage of electronic gearing is that one master can control many followers, and each follower can be driven at a different ratio relative to the master. The gearing function are using in different applications such as gantry axes in the CNC machines, where a beam moves typically by two motors synchronized precisely. Electronic gearing is often used in precise assembly processes that are carried out by a robot following a conveyor, which requires that the robot's speed and position be locked to the conveyor movement. Applications that involve two separate linear or rotary components moving in synchronization, such as flatbed continuous cutting on conveyor, also benefit from the electronic gearing, and specifically from the ability to vary the gear ratio electronically without requiring downtime to adjust the gear ratio manually. Electronic gearing function is widely used to make positional correction of geared color printing rollers on web-style offset printing machines, where material being pulled through several printing rollers, each a different color. The second and third rollers are geared to the first one with the 1-to-1 ratio. This slide shows the same system as previous slide with three additions. First, the master axis lays down a marker in the margin of the material, establishing a reference. The last two additions include two sensors to read the marker, one before each of the slave axes. The system is then designed based on the calculations, assuming no material stretch or compression, since all distances between color rollers are known along with the radius of the rollers. As the marker passes through the first sensor, color roller 2 can adjust its position or phase. Adjusting its phase will enable color roller 2 to properly align its angle so that as the marker passes through the roller, the second color will properly align with the first color. Likewise, the same principle can be applied to color roller 3. This assumes that all rollers home to a known position before starting the operation. In trio controllers, there are simple commands the slaves can gear to the master and correct themselves. Using connect command, which gears the slave rollers to the master roller with a flexible ratio based on the motor's encoder resolution, and the mechanical ratio which gears the rollers 1-to-1. Using the regis20 command to capture the value of theta position on roller based on sensor activation by mark, and correct the synchronization angle by using the additional axis command to superimpose the additional virtual axis to make a correction individually on each slave roller based on captured mark position to calculate the position correction offset. In this part, we will show you how the gearing function operates by using a real EtherCAT axis installed on Trio 3-axis demo kit. With a double axis drive control one motor with 20-bit encoder and one motor with 23-bit encoder resolution, and a stepper axis with 12,800 counts per rev, which uses as a master axis in this demonstration. After enable the gearing function based on a specific gear ratio setting for each slave axis that scale 1-to-1 rotation on wheels because of difference between motor encoder resolutions, if you spin the master axis, both slaves spins 1-to-1 as you see here. If I increase the gear ratio 10 times on axis 1, and if I try to spin the master, axis 1 now spins 10 times faster and more displacement than master axis. We can freely cancel the gearing function by disabling the gearing buttons or by program, which gives flexibility to meet the different applications requirements. Thanks for watching this video.